Okay, so last time we just started the cross product with two vectors in space. In 3D space, we define the cross product from the determinant of 3 by 3 matrices. Okay, use the rules for matrices to compute the cross product. That's a convenient way to do it, and there's some properties we already discussed. Uh, a bunch of rules we have for the numbers don't work for cross product. The commutative law doesn't work. The associative that doesn't work, but the distributive law works. Okay, so let's see, and uh, the uh, the three unit vectors now x, y, and z directions, I, j, and k. They uh, obey right hand rule. Okay, so if you point your thumb uh, on the positive z direction and you hold your fingers, then your fingers should curve from x-axis, positive x-axis, to the positive y-axis. In that way, rotating that way. All right, and then let's talk about cross product properties a little more, and some of them are really a little tricky, and I don't require you to memorize all of those rules. When you use more and more vectors, you get more familiar with those. So let's discuss some general properties of cross products. So suppose there are three vectors, A, B, and C, and the capital C is a scalar, it's a number, okay. And then A cross B is not equal to B cross A, instead it's equal to negative B cross A. So when you change the order of cross product, you get a negative sign. That means because cross product gives you a vector, it's a A cross B is a vector. And the negative sign in front of the cross product of B cross A essentially means you switch the direction. Okay, you still get the same magnitude for A cross B and B cross A, but those are the two vectors pointing in opposite directions. A cross B and B cross A. Those are two vectors pointing in two opposite directions. That's what it means by the negative sign. All right. So make sure you understand what it means for the formulas, as it says. Okay, if you multiply scalar C with A and cross with B, then you can take out the scalar and just multiply this scalar capital C with A cross B. Or you can move the scalar into C and to get A cross capital C times B. And that really doesn't change the result, okay? As long as you have a scalar in the multiplication or in the cross product, it works fine. You can move it anywhere as you like. Okay, and the third property says A cross B plus C is equal to B plus A cross C. So the distribution works, okay, for the cross product. Similarly, A cross B cross C, A plus C cross A plus B cross C is equal to A cross C plus B cross C. So that's another format of distributive law. Okay, so the distributive law works for the cross product. Okay, the next format is very interesting. We got both dot product and the cross product at the same time. So we got B cross C, the cross product between B and C, which gives you a vector. So you can take the dot product of this vector with vector A, And it turns out is equal to A cross B dot C. Okay, so um, what should I say about this? As long as you keep the order the same, A, B, and C in the sequence, A, B, C, then you actually can switch cross and dot. Okay, or you can put C in the front to get C dot A cross B. Okay, so that means you can rotate those vectors A, B, and C in this product, dot product. Actually, it's called the triple product because you got three vectors and you got both dot product and cross product. All right. So, okay. So that's this. And the last formula is a little more tricky. We got two cross products. Okay. We do B cross C first, and then we do A cross B cross C. So B cross C gives you a vector. Then you can take the cross product between A and that vector. And then you're going to get another vector. And it turns out this, cross product, double cross product, is equal to B times A dot C minus C times A dot B. Okay. Remember, A dot product gives you a scalar. So A dot C gives you a scalar. So you get B, which is a vector times a scalar. So that's still vector. And the minus vector C times A dot B, but A dot B again is a scalar. So you multiply that with C, you get a vector. So you get two vectors to subtract on the right hand side, which gives you another vector. All right. And that makes sense because on the left hand side you got cross product. After a cross product, it will give you another vector. Okay. So at least everything is consistent. Okay, but these are some formulas you might use later, but maybe not now. So these are some important properties of cross products. And so let me just focus on this triple product, A dot B cross C. Okay, and see what we can do about it. We call it triple products because, as I said, we have three vectors, A, B, and C, and it involves both cross product and dot product. Okay, so we have the three vectors, A, B, and C, with components A1, A2, A3, B1, B2, B3, and C1, C2, C3. And then we form the triple product A dot B cross C. And if you use the matrices, if you use matrix to represent the cross product between P, B, and C, and then you take the dot product of A with that, and it turns out then you're going to get a determinant of a matrix A1, A2, A3, B1, B2, B3, C1, C2, C3, and they will give you a scalar. Okay, because all of those components, A1, A2, A3, B1, B2, B3, and C1, C2, C3, they're scalars. And that should be the case because on the left-hand side, we got the A dot B. So that's a product. I mean, A dot because C, that's a dot product. Although B because C is a vector, we got the dot product on the left-hand side. We should get a number, a scalar. It should not be a vector, in other words. And this formula just tells us how to calculate the triple product. You just take the determinant of the matrix A1, A2, A3, B1, B2, B3, and C1, C2, C3. And you should not get it wrong for the rows and the columns, okay, for this matrix. All right, so that's how we compute the triple product of three vectors algebraically using matrices or determinant. But then what it means geometrically for this triple product. Okay, it turns out that the absolute value of the scalar triple product, okay, it gives the scalar, the triple product. So the scalar triple product, so we call it triple product or scalar triple product of A, B, and C gives the volume V of the solid formed by the three vectors A, B, and C shown in the graph. Okay. So what do? You just use the vectors A, B, and C to form a solid like this with the parallel planes. So you got something like a box, a skewed box or something, using those three vectors. We know when you have two vectors, you can form a parallelogram, right? Using those two vectors. When you have three vectors, then it gives you the volume, the volume of this skewed box. When you have two vectors, the cross product of two vectors, it gives you the area of the parallelogram formed by those two vectors. So the product gives you the volume of this box. And it's easy to see, okay, if you look at the graph, we have B and C on the base plane, and A has some angle between, with that plane. And we know when you take the cross product of B and C, you get the vector perpendicular to the plane of B and C. Remember? So then suppose the angle between A and B cross is theta, shown in the graph. Then the volume of this box is just the area of base times the height. Okay, so what's the area of this base? It's just the magnitude of B cross C. Remember, we got parallelogram in the base plane formed by B and C. So B cross C, the magnitude gives you the area of this parallelogram shown in the red dots. And then the height of this box or skewed box is just the magnitude of A times cosine theta. Remember, cosine theta is defined as adjacent to the hypotenuse, right? So the hypotenuse times cosine theta gives you the height if you take the absolute value. Okay, but then if you consider A and B cross C as two vectors, as shown in the graph, then the whole thing is just the magnitude of the two vectors A and B cross C, the dot product of those two vectors. Okay, remember when you try to calculate the A dot B cross C, or the dot product of two vectors, you can use the formula of the magnitude of those two vectors times the cosine theta, where cosine theta is the angle between those two vectors. And this is exactly what we have. We have the magnitude of B plus C, we have the magnitude of A, and we have cosine theta, where theta is between the two vectors A and B cross C. But we are talking about the volume, so we should always keep the positive sign. So you just take the absolute value of this dot product. Okay. So in other words, we have shown that the triple product gives you of three vectors gives you the volume of the skewed box formed by those three vectors. Okay. So so this dot product and then cross product and then the triple product all have some geometric interpretation. Okay. Okay, let's see what can we do about triple product. We can find the volume of the box of the from the three vectors a, b, and c. But what happens if three vectors a, b, and c are coplanar? That means they are on the same plane. Then you don't have a box. When all the three vectors are on the same plane, then you cannot form a box, or the volume of the box will be zero, right? In that case, so that means we can use the triple product to uh, to show three vectors coplanar, okay? Because you know the triple product will give you zero in that case. If the three vectors are coplanar, they are on the same plane, then it cannot form a box, or the volume of the box will be zero, in other words. So let's just show that vectors A, B, and C are coplanar, where A is 1, 4, negative 7, B is 2, negative 1, 4, C is 0, negative 9, 18. We want to show these three vectors are coplanar. So we just do the triple product. So that's the easy way to do it. And there are some other ways to do it, but this is one way to do it. So let's just do the triple product of A, B, and C. It really doesn't matter. You do A dot B cross C, or C dot A cross B, whatever. It doesn't matter. Okay. In this problem, okay. In any case, you're gonna get the volume. You're gonna get a zero in any of those triple products. So use the formula for the triple product or scalar triple product. Use for the components of A on the top, followed by the components of B and the components of C. So we get 1, 4, 7 in the first row, 2, negative 1, 4 in the second row, and 0, negative 9, 18 in the third row. And if you still remember how to compute this determinant of the matrix, you can expand this determinant by the first row. So you're going to take 1 times the determinant of the 2 by 2 matrix, negative 1, 4, negative 9, 9, 18. And this matrix comes from deleting the first row and the first column. Okay. And then minus the second entry in the first row, which is 4. And times the determinant of the matrix 2 by 2 matrix 2, 4, 0, 18, which comes from the deletion of the first row and the second column, as were 4 seats. And then you plus the third entry in the first row, which is like 7 times the determinant of the 2 by 2 matrix 2, negative 1, negative 9. I should not be 9, right? Okay. Sorry about this typo. So, again, this 2 by 2 matrix 2, negative 1, 0, negative 1, it comes from the deletion of the first row and the third column. Okay. And then you just do the determinant of 2 by 2 matrix one by one. So we got 1 times negative 1 times 18 minus 4 times negative 9 in the first term, and minus 4 times 2 times 18 minus 4 times 0 in the second term, and then minus 7 times 2 times negative 1, 9 minus negative 1 times 0. Okay, so again, this should be negative 1 instead of positive 9. So in the first term, we got negative 18 plus 36. Okay, negative 4 times negative 9 is 36. So negative 18 plus 36, 18. And then in the second term, 2 times 18 is 36, minus 4 times 0, which is 0, so we get a 4 times 36. And in the third term, we get 2 times negative 9. Again, it should be negative 18, and then minus 0. Negative 1 times 0 is 0. So minus 7 to the negative 18 is third term. Then we got 18 in the first term, and minus 144. 4 times 36 is 144, and then plus 126. Okay, we got the negative sign 7 times negative 8. If you create this type in here, so it becomes plus in third term. Then you get 18 minus 144 plus 126, and that will be 0. Okay. Sorry about the pad table. So we got the triple product equals 0, which means the volume of this solid skewed box formed by the vectors is 0. So that means the three vectors are in the same plane. They are coplanar. All right. So, any questions? No question. We got one more. One more slides for this side for this section. All right. The last thing is the application of cross product. If you took a physics course, you can physics course now. You should learn that the torque on an object by force F with arm R is equal to the cross product of R and F. Okay, torque. So as shown in the graph, so basically the torque, tells you, how much the force and the for rotation, the measure of this force of rotation. So we need the arm cross the force. Okay. So so in here we got the object, cylinder with some arm R, and then the force F is applied at the terminal point of the arm R. Okay. And then the torque will be pointing to the inside, perpendicular to the plane. Okay. If you use the right hand to figure out the direction of R cross F, it gives you the direction perpendicular to the paper plane. Okay, so let's do one example. Find the torque on the object if the force is 36 pounds and the arm of force, which is R is 4 square root 2 feet. And the angle between the arm of force and the force is 105 degrees. Okay. So we need to find the torque. So that means we are talking about the magnitude. Okay. We're not talking about the direction here. So the magnitude of the torque tau is just the magnitude of R cross F, which is the magnitude of R times magnitude of F times sine theta. Okay. Remember, that's the formula we have. Another formula. For the components, we use the determinant to figure out the torque, but if you are given the two vectors and the angle between the vectors, then you can use this formula to find the torque, the magnitude of the torque. So everything is given here. The magnitude of R is the arm of force is 4 square root 2, and the force is 36 pounds. So and the state is 105 degrees. So it's multiply, plug in those numbers, and then you can find out, sine 105 degrees is actually square root of 6 plus square root 2 over 4. Okay. And 36 times 4 square root 2 is 1 square root 2. And then if you multiply them out, you're going to get 72 times square root of 3 plus 1. If you do a little simplification after the multiplication, you can cancel 4 from 144 to get 36, but then you can distribute the square root 2 to square root 6 and square root 2, and then you can just simplify this a little bit. You get square root 12 plus 2. And square root 12 is 2 times square root 3 if you do it. You can factor 12 by 4 and 3, so you take the root, you get 2 square root 3, and then you factor out 2 and multiply 36, you got 72, but then what is left is just square root 3 and plus 1. All right, so that's the torque in the unit of pound-feet. Okay, any questions? So that's the application of cross product. No question. We still have 6 more minutes. Why don't we just start in the last section? That will be a long section, so we probably need a little time to finish it. So let me just go to the next section, the last section, 11.5. 11.5 is talking about the geometric object and described by using vectors. Okay, so we're talking about two things here, basically lines and planes in space. So we're going to use vectors to describe lines and the planes. And for some of the discussions, we're going to need to use the dot product and the cross product. Okay. So let's start from the lines in space and how we can write the equation of a line in 3D space. We know how to write the equation of a line in XY plane, but in 3D space, how do you write down the equation? Again, let's say given a point P with the coordinates x1, y1, z1 on a line. So that's a line in 3D space. And we have vector v with the components a, b, c parallel to the line. Okay, so you cannot talk about slope in the 3D space, but you can use the direction vector. Okay, we call this v and direction vector. We know this line is parallel to this vector v given in the problem, and the point P is on the line also. That's also given. So we need to find the equation for the line. So that means for any point Q on the line with coordinates x, y, z, what's the equation those x, y, z have to satisfy in order it to be on the line? Okay, so that's what it means by the equation in 3D space. So again, let Q be any point on the line, then we can draw a vector from P to Q, and this will be parallel to the vector V as given in the problem. So if two vectors are parallel, then we can write one vector as scalar multiple of the other vector. Okay, what you do, you just change the length, in other words, of the two vectors, but the direction keeps the same. So that's how you write two parallel vectors, right? Okay, and then what? You just either shrink or extend of the vector to get another vector. All right, so that's why you get T multiply the vector V, the direction vector V. We don't know what T is, but we know it has to be like this, okay, because they're parallel. But as we know, we can use the components to describe the vector PQ. You just subtract the coordinates components so we get x minus x1, y1 minus y minus y1, z minus z1 for the components of PQ. Remember, terminal point minus initial point. Okay, and That's the vector PQ, and it has to be equal to T times V, as we said. So that's T times ABC, where ABC are components of V. Use properties of vectors, we can distribute T inside the components of this V. So we get a TTBTC. Now then we got two vectors equal, and the components have to be equal for each component. Okay, so we get x minus x1 equal to T times A, y minus y1 equal to B, z minus z1 equal to T times C. So if you rewrite those three equations by moving, x1, y1, z1 to the right, you're going to get x equal to x1 plus at, y equal to y1 plus bt, z equals z1 plus ct. So this is a parametric equation for the line. So we got three equations. So it's a parametric equation for the line. In 3D, we got three parametric equations specifically because we got three components. Each of them is a linear equation of T. Okay, and T is a parameter for this parametric equation, right? We talk about the parametric equations in two components, x equal to f of t, y equal to g of t. That's in the plane. Now we got the object, the line, in 3D space, and we need the three components, x, y, and z, and all of them are linear functions of t, and we just need another dimension. Okay. But you can also write this parametric equation in another format. So if you subtract the x1 in the first equation on both sides and divide by a, you get t. And you subtract y1 on both sides, second equation, and divide b, you get t also. And you subtract z1 on both sides of the third equation, divide by c, you get t. So you just solve t from each of those three parametric equations. But t should be the same. This is the same parameter we use to describe this line. So then x minus x1 over a has to be the same y minus 1, y minus y1 over b, and equal to z minus z1 over c. So because all of them are equal to t. So this is called the symmetric equation for the line. So this is not the format or form of the equation of a line in 3D space. Okay, so and as called the direction vector, and the ABC are the direction numbers. Okay, I just want to this t takes the value from negative infinity to positive infinity. As you change the value of c from negative to positive for all the numbers, all real numbers, then you're going to get all the points q on the whole line. So so that's the and in 3D space, how we use vector to describe a line in 3D space. And we're gonna talk about more about this topic next time. Hopefully finish the whole thing in the next class. Any questions about this? So it becomes a little more complicated. Okay, you can see the graph. It makes it easier when you draw the graph. Okay. Okay. No question. Let me just stop the recording, and we're gonna continue from here next time.